Okay, so today today we're going to cover chi-square, okay, a chi-square test. So up to now, we've done correlations. Correlations are between two types of what variables? That's the t-test. Correlations between two continuous variables, but good, at least you had the category wrong name. So hey, okay, so again, just think about the types of variables that we can encounter. Two continuous correlations. One is a dichotomous, a category, yes, no, 0, 1, and another one continuous, t-test. Today, we're going to, the chi-square is two categoricals. Okay? So with that said, let's get started. Now, the interesting thing about this class, as every class moving forward, we will be doing everything in both SAS and R. Whether the assignment is in SAS and R is a different story. But so this is starting because this is a requirement, or let's just say an ask from the SAS people. They said, well, fine, if you're going to have an assignment in R, it's fine, but at least show them both ways. I'm like, can't hurt. And it's actually, I like that because a lot of discussion in industry when people want to transition from SAS to R is, but are the results going to be the same? They've got to be the same because neither the person that wrote the code to do a correlation in R, nor the ones that wrote the correlation, the code for correlation for SAS invented the correlation test or the t-test or the chi-square test. They took that from an algorithm that already exists. Think about an average. If you calculate an average in Excel or in R or on your calculator or by hand, the result should be the same. Okay? If it isn't, it could be a rounding, rounding of decimal points. But if it's significantly different, then there's a problem with one of the methods or both. Okay, so let's go to SAS. So we're going to start out with SAS. And I'll get you, well, you guys already have access here to this. So anyway, I have this data set cheater, which is basically the FAIRS data set with a dichotomous variable that's cheater, 0, 1, okay? And one question, what can we compare? What other categorical variable can we compare it to? What are you interested in knowing? So I want to know if people cheat or not cheat, if that has any relationship with what variable would you like to know if it has a relationship, a categorical. So which categorical variables do we have here? Gender, categorical. Children, and occupation is a category. Okay, so what do you, between the variables gender, children, and occupation, what do you find most interesting to know if there's a relationship between cheating and what? And gender. So How many people think that, well, raise your hand if you think that men cheat more than women. It's okay. So all the other ones are abstaining, or do they think that women cheat more? Okay, we have one women cheat more. The others, I think, are good in abstaining from all comments. Okay? So let's run this test. So to run this test, who can tell me where I can start finding where the test is? Where is the first place I need to start looking for the test? Here in SAS. Task and utilities. And then statistics. And let's go here to table analysis. Okay? So in table analysis, there's a lot of stuff that we can do. Okay? So what do we want on our rows? Do we want, it's not a trick question, okay? What do we want on our rows and what do we want for our columns? So think about how this is going to be organized. Two categories. One is the column, one is the row. How do you want that organized? It's not a trick question. Or gender. Gender as columns. Okay, so I'm going to go to columns, hit the add sign, and I'm going to click on, where is gender? Oh, I don't have the right data set, sorry. You have to choose your data set. I'm going to go to my library 560. I'm going to choose my cheater data set. Click OK. Okay. Now, so for the rows, that means that we're going to want cheater. And for the columns, we're going to have gender. So then I'm going to go here to settings. Okay. So in settings, we have this. And I'm going to go to options. So I'm going to click on this, on row and column, okay? And then in statistics, I have chi-square statistics, okay? I'm actually going to click on this as well, okay? And let's just see what this gives us. And I'm recording this and I will upload this to YouTube and then put in the link. We're going to run this. I just want to see what's going to happen here. Here are my results. Hello. So don't worry, everything is being recorded here. Okay, so that, here we are. And let me just minimize this. So let's take a look at what this table has, okay? The first thing, as usual, we want to, these graphs, don't worry about them. The first thing that we want to look at is a chi-square test. So we're doing a chi-square test, and we want to look at our p-value. What does that p-value tell us? If my alpha, meaning the bar that I'm setting for this test is 0.05, and the p-value came up to be greater, 0.216, what does that tell us? Is it significant or not? I can't hear. Not significant, great, okay. Seriously, I couldn't hear. So, end of story. That's it. If it's not significant, there's nothing else for us to look at. It's that simple. We can look at more stuff. But what we're going to say, and when we go into R, we're going to show you, I'm going to type in what I would say, what I would exactly write here, is that there is no dependency between cheating and gender. You guys with me? Sorry. If you think about it, in a heterosexual relationship, to be able to cheat, you need a man and a woman. Okay, there's two participants. Okay, so when this doesn't come out, when gender doesn't come out to be significant by itself, there's a logical explanation to this. Because remember, we need to say, does this make sense or not? And well, I guess you need two. And not necessarily the other partner, when you're cheating, is going to be single. So in other words, okay, there we go. So let's take a look at this table. And to be able to read this table, we'll run another test, and hopefully it comes out significant and we can start describing the relationship. But the way we see this is that we have a legend right here. It says frequency, cell chi-square, row percent, column percent. So in other words, there's 243 females that cheat or don't cheat. That don't cheat. This is cheater 0. This is female. There are 208 males that don't cheat. 72 females that cheat. 78 males that cheat. Well, given that I'm looking at the way this table is organized, I am more interested in the column. So I gave you guys to choose the setup as rows and columns however you wanted to. I would keep it consistent. Because if you keep it consistent, you're going to know what matters most, rows or columns. The way this is set up, the column is what matters. And I'm going to explain why. Because the column is the column percent. Look at this, 77.14 plus 22.86 sums up to what? Lucky guess, come on. 100. So 22.86% of females cheat. 27.27% of males cheat. Who has a higher proportion of cheaters? Huh? Males. Okay? So think about how interesting what we've just done here. I think it's interesting that you could have added up all the proportions without doing this. You could have done this in Excel, okay? And say 22% of women cheat, 27% of men cheat. Right there, you'd say men are more cheaters. They're bigger cheaters. But what this test is telling us, when we go down and take a look at our p-value, is that at the alpha 0.05 level, the difference is not significant. That's why we use statistics, because you have a 22% and a 27%. If you do a bar chart, 22 versus 27, there's a difference. But is it significant? Statistically significant? No. How could it be more, how could we perhaps make it, how can it possibly be more significant? Why did it not come out to be significant? Being such a big difference, 22 versus 27, it sounds like a big difference. It's the number of total observations. We only had 600 observations. It wasn't enough for this test to conclude that the difference was significant. So, as a researcher, I would say two things. There is no dependency between gender and cheating. Second, maybe there is, but we would need to survey more people. So if for some reason, something in the theory of, in the body of knowledge of the world, it says that men are bigger cheaters, well, the only thing that we can do at this moment is say, let's survey some more people. Okay? Okay, I'm going to switch over to R because I want to, well, before we do this, no, let's do this, let's switch over to R just to run this exact same test, okay? And see if the numbers are the same. So allow me a second to get the new RStudio window. Let's start out clean here. Okay, so I'm going to bring in the file that is up on Canvas. And now we're in fall. Okay, so let me load my packages. So for today's class, hold on, I need to install a library. So the main function that to do the chi-square test is this one, the G models, okay? I am using today the library AER because I want to show you guys where I got this data, okay? This data actually, again, comes from a survey done in the 60s, a study done in the 60s. But the data comes, I got it from this package called AER. So here I'm creating my variable cheater. And today I actually decided to not make it a 0-1 variable. I'm calling it cheater and faithful, okay? In occupation, I'm making it as a factor. Well, it's better for, you don't have to for the G models, you don't have to, but it's a good practice to do if it's categorical. You can just do, you see, if I did, you see I just did this function freak cheater. This comes from the package fun modeling that produced these graphs for me. And if I label it as a category, okay, as factor, it produces, it gives me these summary statistics, okay? Anyway, so let's do the test of cheater versus gender. And so I just ran this. I'm going to expand my window. So first of all, let's take a look at the p-value. 0.211596. Okay? 215596. 2116. It rounded. Okay? Are we good? Look at this one. The continuity adjusted chi-square. This is another p-value that it's being cut. 0.2482, 0.24816. As you see, we've got the same values, okay? Look at this table that gets produced. It looks very similar to the table produced in R, okay? Here we have cheater, faithful, okay? Female, male. Why is my cheater on top and faithful on the bottom? While in SAS, the faithfuls were over here and the cheaters were down there. Why? Why did it organize it that way? Huh? Alphabetical order, okay? But anyway, the percentages are the same, okay? 72, 78, 243, 208. '72, '78, 243, 208. Same thing. Look how, obviously this table looks a little bit nicer than the one produced in R. However, again, the people that developed this in R, this package, they did it with the intention for it to look like the SAS version. It just looks right. It's easy to interpret, okay? The 22 versus 27%, okay? It's all the same. Now, again, so if I go to my code, you're going to see my explanation for this test. There is no dependency between cheating and gender at the alpha 0.05 level. So how can we put this in layman terms? How would you explain it to your next door neighbor? Well, tell me a little bit stronger. Say it in a way that everybody's gonna understand. Is that how you talk with your friends? Think about how you talk with your friends. They say, no, men are cheaters and this and that. And you gained this knowledge today. And how would you tell them not true? Think about it. You're at a party and men are such cheaters. And you say, not true. What are you going to say? Women are more cheaters? What are you going to say? Doesn't matter. Gender doesn't matter in cheating. Okay, just say it. Think about you're at a party, you're talking with a friend. How would you explain it? So, how about this? When it comes to cheating, gender doesn't matter. There you go, done. Okay. So let's do here another one, okay, which is cheater and children. Okay, let's go to SAS. Okay, go here to settings. I'm sorry, to settings and data, and let's take out gender. And what was it that we're going to do? This is children. Okay. So what do you guys think? If you have children, are you going to cheat more or less? Who are the bigger cheaters? People with children or without? Well, it depends on what. Well, that's a good explanation. Look, I've studied this data set a lot. And for me, a cheater is a cheater. You know, it doesn't matter. But anyway, what do you guys, give me a guess. So your guess is that it's not going to come out to be significant. Anybody have any votes? Not significant? Or who thinks that if you have children, you're going to cheat more? Okay. Okay. Look, this can go either way. Let's run this. Oh, I'm sorry. Let's look at options here. And I'm actually going to want to take out the plots. So with the plots, suppress plots. Let's run this. Okay, let's go to results. Okay, let's scroll all the way down to find our, let's find our p-value. Where the hell is our p-value? There we go. Well, look at it. There's a dependency. At the 0.05 level, there's a dependency between cheating and having children. What came first, the children or the cheating? In this data, children come first. Now we've established a temporal difference, okay? Now we can actually say that maybe children can cause cheating. So 3 things need to happen for causality. No, I'm serious. This is the world of research. There needs to be an association. We've established the association right here with this p-value. There needs to be a temporal difference. Children came first, okay? At least we suppose that in this data set. And then it needs to be grounded in theory. So there needs to be something in the literature that says that, yes, you know, people with children, I don't know, something, okay? We can rationalize this in some other way. I don't want to, okay? It's gonna get into touchy subjects, okay? So, well, let's take a look. So, our area of interest is this cell over here, the cheater and the yes with children, okay? That's, or the no, let's see, which one cheats more? People without children, look, I'm looking at the column percent. Look, 1, 2, 3, 4, so it's 1, 2, 3, 4, the last value. 84% of people without children don't cheat. Close to 16% of people with children, I'm sorry, without children cheat. People with children, 71% are faithful, 28% cheat. Now that's 15, close to 16 versus 28. Now that's a big difference. Okay, are you guys with me? Okay. So let's take a look. So we know it's significant. Okay. Now we're going to take a look at other calculations. Look at what I have here. I have relative risks. I have an odds ratio. Anybody have an idea how these odds ratios are calculated? Or relative risk? So let's figure this out. We have this relative risk of 0.83, okay? Any ideas how we got to 0.83? What numbers do you think got divided here? All right, guys. I'm sorry? Cheater. Okay, let's not guess it. Are you guys here? Look at this. We just divided these two. Divided these two. Okay? Hold on. Risk ratio, risk ratio. Go here. Just want the formula. Okay, it's got it by dividing the probability of an event occurring for group 1 divided by the probability of an event occurring for group 2. Okay? So, back to this. It depends on how your test is set up. So, the way this test is set up, what is the risk of cheating if you don't have children? What is the risk of cheating if you don't have children? 16%. Okay? That's the risk of cheating if you have children, if you don't have children. The risk of cheating if you do have children is 28.6. The relative risk relative to each other, you would divide this divided by this. Okay? So let me go back because again, the way relative risk is calculated here is, it just depends on how things are set up. Okay? One 1.7, 0.8. Let's go here to ours here. Here I have this. Look at how you would calculate. People with children are 1.8 times more likely to cheat, or the relative risk is. So look at the risk of cheating if you have children, the risk of cheating if you don't have children. Okay? $1.8. So to calculate odds ratios, again, you want the test set up exactly. Okay, I ran this here. Here I have cheater. I actually would like the children to be right over here. Okay. Personally, I rather, because I want my event of interest here in this cell. But anyway, that way the odds ratio would be calculated a lot easier. But anyway, the way odds ratios are calculated are this times this divided by this times this. Okay? Let's do that calculation. 123 times 144. Hold on. 123 times 144 divided by 27 times 307. Yes, that's right. Thank you for that. I know something didn't look right there. Okay, 2.13. Okay, those are my odds. Okay, my odds of cheating if you have children. The odds of cheating are 2.13. That's an odds ratio. Let's go back to SAS. Let's see if they came out with. Look at this number right over here. Same number? Now, I'm going to tell you how we came out with the same number. Okay? The only reason why we came out the same number is because this table over here is inverted as to having this as your reference point, because it's saying this is your reference point. Anyway, it doesn't matter. But again, my event of interest, okay, here is this one. So if this is my event of interest, I do this diagonal divided by this diagonal. Just find wherever your event of interest is. Do you guys understand why I said this was my event of interest? Why did I say this over here was my event of interest? One, because it's cheaters. And two, because it's with children. Okay? That way I can say the odds of cheating, event of interest cheating, if you have children, again, event of interest, is 2.13. The odds of cheating are 2.13. And again, this is where, if you have children, this is where sports betting comes in. When they talk about odds, this is it, okay? Where are the odds? I'm sorry?
I was just thinking, is it the odds, I mean, would it put it like this, that odds of children, odds of people who have children, see 2.7 times
No.
the odds of children.
Sort of. It's a You see, we talked about, so I know it can be confusing, the relative risk, okay? Because the risk of cheating, if you have children, is, you know, is 1.8, meaning that you're more likely, you're almost twice as likely to cheat if you have children. We're talking about relative risk. The odds of cheating are 2 times, given it 2.13. Again, the odds is just a slightly different calculation. I'm not articulating it well right now. Sorry.
I mean, odds I was always assuming that they are like two dependencies that odds are calculated.
There is a dependency, yes.
Odds are calculated like, odds of this happening is
twice as likely.
Of this event not happening or this event happening with them?
You are twice as likely to cheat if you have children as opposed to if you didn't. So in sports, what are the events here? In sports, you have 2 teams. Team A, Team B. Lose, win, lose, win. Kind of good? Kind of okay? Well, the main thing is this. I'd rather you guys stick here with the relative risk, okay? Let's just go easy on this, okay? Now, let's run this one, okay? The p-value came out to be not significant, occupation, okay? Let's do this in SAS. I'm sorry, settings. Oh, not good. Sorry. So I want to go through this table, create this table with occupation, because this is a unique situation that you're going to encounter in your homework. And the situation is as follows, that how many levels of cheating do we have? 2. Either you cheat or you don't. Occupation, we have 7 levels of occupation. So what that says to me is that it's not that straightforward. There's not just 2 categories that we can compare. So let's look at our results here. Oh, did I not run this? Cheater, occupation. Not letting me run. It's not probably not letting me run this because it's not seeing it as a category. Best plots. No. So let's just do this in R. So in R, this is what happened. Because you guys are going to do this on the variable called sales, which in reality are departments, okay? And you're going to have multiple levels. So imagine for a second that this came out to be significant, okay? The limitation, not a problem, the limitation that you have here, okay? And look how I reorganized this. I put cheater as a column. Why did I put cheater as a column instead of as the row? It's just for visualization purposes. I'd rather be able to scroll down. So now I'm interested in the row percent, okay? So 20% of people in occupation are cheaters. 23% in occupation 2 are cheaters. 31% in occupation 3, 30% here, 21% here, 27, 38. What's the problem with, why do you think this didn't come out to be significant? We have pretty big differences. Between 23 and 30, there's a big difference. And between 23 and 38, there's a huge difference. Why did this not come out to be significant? It all boils down to, we're only dealing with 601 observations. And in this category, where 38.5% are cheaters, it's only 13 people. You can't make an inference about the entire population of the world by just 13 people. It's just very weak, okay? It doesn't matter really that it's only 2.2% of the data, because when you're dealing with millions of people, 2.2% is a lot of people. But when you're dealing with 601 people, it turns out to be, we have 5 cheaters and 8 are not cheaters. You see, this is basically the basis of discrimination. This is how discrimination, prejudices. Do you know what a prejudice is? Think about the word prejudging people. So many times, you see, when I grew up, you guys are from India, right? When I grew up, you know, my early years on Long Island, New York, I did not know a single person from India. Not a single person. Well, this is back in the previous century, okay? But there, on my street, in my school, I had no idea anybody had Indian parents or anything. So imagine that I would meet one Indian, okay? And it just so happens that that Indian was a nasty person, right? And then I walk around saying, I don't like Indians. You're basing it off of one observation. You can't do that. Us as humans, we tend to do that. And that's a bad, bad thing. If I know 2 Indians and they're both not nice people, should I say that all Indians? How many Indians are there in the world? 1.3 billion. Okay, so do you see, not good, okay? I need to know more Indians before I can make a judgment call. And how many do I need to know to make that judgment call? I don't know. Well, that's why we like using statistics. Well, you know, so you know, if I end up meeting, you know, 100 Indians, okay, and I can say that so many are not nice and so many are nice, then I can say, well, is there a dependency of being nice or not nice with being Indian or not Indian? That means I have to survey other people that are not Indian. You see where I'm going with this? You need to have a comparison. So we need to have people in both sides, okay, Indian and not Indian. With that said, aside from picking on Indians, you know, it sounds like I'm a comedian, because comedians pick on everyone. You know, they don't leave anybody untouched. Indians versus not Indians. If this came out to be significant, okay, what other categories of people can I have if you're not Indian? Being Indian is what? Would you say it's a nationality or a culture? Let's just if you want, let's keep it at nationality, or if you want at culture, it doesn't really matter. Because the thing is this, if we keep it at nationality, that's fine. How many different people that I know, how many national origins are there? Probably many. Italian, Irish, whatever, okay? So if this were to be significant, this p-value, then I would say that there is a difference between being nice and not nice, depending on nationality. Which one is nicer? Well, I can take a look at these percentages that I'm looking at, okay? If this came out to be significant, I would report that occupation 7 seems to be more cheaters. But you see, seems to be. This test, when you have more than 2 categories, you're not allowed to pinpoint which one is more and which one is less. And I'm going to tell you why. Because here I have a 38, right? Here I have a 27, 21, a 30. Is 30 really different from 38? We don't know. How about the really non-cheaters? Here's a 20. Well, here's a 23. 31, 30. Here's a 21. Do I lump the 21 together with the 23 and the 20? Are they all the lowest cheaters if this were to be significant? You just don't know. So if it's significant, you just report there is a dependency between occupation and being a cheater. It seems to be that the less cheaters are occupation 1, 2, and 5, okay? Or you can say it seems to be that the most egregious cheater is occupation 7. However, we don't know if we should lump in another category. The way to do it, to pinpoint a single category, you need to go back and redo the test. But before you redo the test, you need to lump in all the other occupations into an other category versus occupation 7. And if you think that maybe occupation 4 with a 30 should be together with 7, then you should do occupation 4 and 7 versus all others. Are you guys kind of following where this is going? So to really pinpoint where it is, you need to manipulate the data again and redo it. I'm not asking you guys to do that in your assignment, okay? Just have the experience of doing a chi-square test where you have a 2 by more than 2 table, okay? That's it. Tell me questions, that's good. Well, so that's a great question. Isn't that subjective? That's why I said you first test 7 versus all others. Well, then you've got to test 7 and 4 versus all others. And then, do you follow? Because that exact question, you see, if I were to present a paper or submit a paper to an academic journal saying that I have determined that occupations 7 are cheaters. And they're going to say, well, they're going to want to see all my background as to why I did that. And they're going to see this big table. And when they see this big table, they're going to say, did you test 4 and 7? That better be in my paper saying that I also tested 4 and 7 and it came out not to be significant. Oh, okay. So you did do it. So yes, you've got to try it from all angles. And when I say that I tested that, and I'm talking about an academic journal, but you guys, most of you, if not all of you, will not become academics. So what does this mean in the business world? In the business world, well, look, quite frankly, you're not a an academic and you ask that question. So somebody in that presentation is going to ask, did you test that? That's in your appendix. Yes, I did. Did you really? You scroll all the way to your appendix in your presentation? Yeah, here's the test. Oh, okay. You covered all your bases. And I would say that, you know, some people in the world, both in academia or in business, will say, well, in business, things are more loosey-goosey. Well, maybe, maybe not. Because you know what? There's always going to be somebody in the room like you that just asked that question, if they're actually following the presentation, okay? So not necessarily. And it's upon the person doing the analytics to say, yes, and through these differences are significant, so forth. And let's just say if we go back to the gender one, okay? And somebody says, yeah, but still, the percent of cheaters of females is 22, I mean, it's 23% versus 27. That is a difference. If we do the relative risk here, it's going to come out to be 1.2 something, okay? Well, it's your job to say, my friend, the p-value came out to be not significant. However, if we surveyed more people, given that the p-value is not 0.9, you know, some really huge number, it's 0.2. It's 4 times my alpha, 0.05. Well, maybe, just maybe, if I had more data, it would work. Okay, to demonstrate this to you guys, let me see how we are on time. Well, if not, I'll just do another Zoom meeting. To demonstrate this, I'm going to take this data, these 601 observations, and we're going to stack it on top of each other. I'm going to make a duplicate to stack the two data. So I will have 1,204 observations, identical. I'm just duplicating the data. Let's do that, and I'm going to do that demonstration. Because it is important to, hold on. So let's create a new data set. Why isn't this allowing me to write it here? Okay, so I'm going to call this double. Double C for double cheater. Okay, so I'm going to do this. Row bind, R bind cheater, comma, cheater. So I'm doing row binding cheater and cheater. Okay, if I look at the data set double, now it has 1,202 observations. Okay, I'm going to take my test over here. I put it over here. I have to change the data set to double C. Let's run this. Look at my p-value, 0.07. It went from 0.2 something. Look at my proportions. They're the same proportions. It's the same data multiplied times 2. The proportions aren't going to change. Okay? Yet my p-value went to 0.07. So that means that if I do triple C, so let's call this triple C, So I'm tripling the data now. So let's run this. Okay, look at my p-value, 0.03. Now it's significant. Look at the proportions, the same exact proportions. I'm just tripling the data, okay? Yet, now it's significant. Now, I can go back to my boss and say, look, if you're really adamant about me proving this, if we survey another 1,202 people, another 1,202, and this initial 601 was really a true representation. That means I do this 2 more times, I'm going to get the same results. And if I do get the same results, this is now going to be significant. Are you guys with me? There's one little caveat here, and I'm sorry. This is a discussion. In academics, then we start talking nonsense, okay? And, you know. Right now we tripled the data set. We have 1,803 observations. Right here. I can see it right over here. Is a p-value of 0.05 still adequate with 1,800 observations? Maybe, maybe not. I think that at 1,800, we're at, look, if you have a bunch of statisticians in the room, if you have 2 statisticians, you're going to have 2 opinions. If you have 10, you have 10 different opinions. If you have 1 statistician in the room, he or she is going to be torn between, I don't know. At that point, I'd be a little bit happier at the 0.01 level. And at the 0.01 level, it doesn't make the cut. So just for argument's sake, let's quadruple this. I'm just going to do it this way. Okay? If I quadruple the data in 2,404 observations, my p-value is not 0.0, it's not below 0.01. So if it were my call, I'd say, you know what, fine, survey another 1,200 people and we'll see. Alpha, I'd like it to be 0.01. So if I survey another 1,200 people, all we need is a little bit more cheaters, proportion of cheaters in men, and this will happen. So that's the discussion as to many people wonder, many people wonder is, how many people do I need to survey? There are calculations for that. But given an initial survey, now you've got a real number that you can shoot for. Okay? The reason why I am touching on this discussion today, as far as the sample size of how many people we should survey, is, or how much data do we need to be able to prove something? Many times you start an analysis with data available in a company, right? You start an analysis. And many times the first pass at that analysis doesn't yield results that are that strong. It gives strong indications of where things may be leading, but there's a lot of messy data, or you need to collect more data. Because what happens is that in companies, it doesn't matter what the company. So you choose any industry. Give me an industry. Give me a company that deals with customers. What was that? A biopharmaceutical. Give me another example, something more common in everyday life for all of you. Amazon. So Amazon wants to know why you guys don't buy more frequently, or what makes you buy more frequently or not. And so what data does Amazon have on you? Your past purchases, okay, fine. But what data does it collect from you that you can give them voluntarily? Maybe some data, okay? Maybe some data. Maybe voluntarily they've asked you, what's your age? Or what's your gender? Voluntarily. But not everybody likes. So as you see, many customers may have some missing data. And you're wondering if age has anything to do with it, or your occupation, your exact occupation, or your household income. You know, sometimes they ask, hey, can you give us your household income? It's voluntary. Okay, so if there's an early indication that these things are important, but like you didn't have enough data, not so many people responded, well, there's an indication for the company to say, push a little harder for this. Give some incentive to your customers to give you this information. And so 3 or 4 months later, there's going to be more data, and you're going to redo your analysis. So what I'm getting at is that this discussion of the gender part, okay? Yes, at the point of this, with this data set, there is no dependency between cheating and gender. However, if you want to push it, collect more data, there could, it seems like if we had another 1,200 more observations, we can make a better determination. Oh, can we do 600? Yeah, we can do 600 more. That means when we had 1,200 observations, the p-value turned out to be 0.07. No? Okay, fine. So, any other questions? Tell me. The alpha is your choice. You see, good question. How do I set the alpha? I mean, how do I make it my choice? Yeah. Okay. It's a judgment call. It's literally a judgment call. Because there are ways that, if you want, we can talk about it offline, that it's called Bayesian statistics. So Bayesian statistics is basically looking at your first results and determining what is an appropriate, let's say in this case, alpha, okay? But the way p-values are calculated, okay? So let's get into this discussion, okay? And with that, we'll finish it, but p-value formula, okay? I want to look at the formula. Because the p-value is going to be, the calculation is going to be a little bit different based on the test you're doing. But this is, look at this formula over here. So the p-value, when you calculate something called one sample z-test, statistics look like this. Da, 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 da. P-value formula wiki. I just want to show you guys one formula. Well, one of uh, well, probably the best one that we had was just know this. In the p-value calculation, somewhere in the p-value calculation, there's a division by the number of observations, the total number of observations, okay? So as you have bigger data sets, if it's getting somewhere, it's getting divided by the number of observations, p-values, no matter what, are gonna get smaller. The bigger the data, the smaller the p-values are gonna be no matter what, okay? Even for very unlikely things to be significant. So in the good old days, 0.05 was pretty good because, you know, when this study was done in the late 60s, when they did the survey about these affairs, interviewing 600 married people and asking them about affairs, if I asked you, any one of you, to say, I need you guys to do a survey with 10 questions, and I need 600 complete surveys, it's going to take you a while to get it, right? 600. Yeah, you guys are thinking, well, I can get 20 done today. Okay. After you've hit your 20 people that you know, get the other 580. It's not that easy. Okay. But in today's world, data has become a lot more available. Companies are huge. They're reaching people, people are fessing up information electronically. So information is getting, generated electronically. So data, think about even, so Max was talking about a biopharmaceutical. Again, they're getting data from claims, from insurers, all electronic medical records. So the question is then 0.05 doesn't cut it, okay? So, well, how about 0.01? Yeah, that usually cuts it, okay? But when you're dealing with millions of rows of data, 0.01 doesn't cut it either. So what you're getting, what you guys have seen in your homeworks that you've done, is that sometimes these p-values are really tiny. 7 times 10 to the negative 8, okay? So these are really tiny values, significant, okay? It goes beyond our comprehension of how small that number is, okay? That's usually a rule of thumb. Are we good, kind of, Max? Okay. Anything else, guys? So let's stop this video. Stop recording.